Good afternoon, everyone. A warm welcome to everyone joining us today for our insightful Maple webinar from pen and paper to modern math tools. I'm Nityashri, data analyst and Maple expert at Binary Semantics, and it's my pleasure to be your host and one of the speakers for this session. We have a truly distinguished panel of experts joining us today. Along with Binary team, it's an honor to introduce Professor Dr. Anil Kumar Gilawat. Welcome to the session, sir. So
Thank
Professor Gilawat is Thank you, sir. Professor Gilawat is currently an assistant professor and training and placement officer in the mechanical engineering department at Rao Birendra Singh State Institute of Engineering and Technology, the Government Engineering College in Haryana. His impressive academic journey includes BTech, MTech, and a PhD at NIT Surat. Professor Gilawat is an expert in robotics applications for prosthetic arms and has been deeply involved in mechanical analysis for the last decade. He is also actively associated with various professional societies, including SAE India and the Institution of Mechanical Engineers, ISTE, and the Association for Machines and Mechanisms. We are very happy to have you all with us today, along with our esteemed colleagues from Binary Semantics. So before starting with the actual webinar, I just want to introduce you all with a short glimpse of our organization, Binary Semantics. Let me just give a brief introduction about the same. Hi, Anagha, can you please let me share my screen?
Yes. Please check it now.
Yes. So to talk about our organization, Binary Semantics, let me give you a brief overview of our journey. For the past 39 years, Binary Semantics has been a trusted partner in the technology landscape. Our foundation lies in deep technological expertise, allowing us to serve global customers across diverse industry verticals. To talk about our technological expertise, we delve with digital transformation, data analytics, cloud and big data, cybersecurity, and smart technologies. And we have partnered with Microsoft, Oracle, Click, SAS, and of course, Maplesoft. And to talk about industry verticals, as I said, we have been with BFSI, transport and logistics, oil and gas industries, and also accredited with ISO certifications, CMMI, and MDESC. Also, we have a global presence at India, Malaysia, Sri Lanka, and in North America, if we say it is in USA and Canada. In deep to talk about our portfolio, it is quite comprehensive, reflecting our commitment to innovation and providing cutting-edge solutions. This includes our suite of in-house products like Visoft, our visual inspection solution, GST Robo, our GST compliance automation tool, Fleet Robo, our intelligent fleet management system, and our robust business intelligence solution that empower data-driven decisions. We are also deeply invested in edtech solutions, recognizing the transformative power of technology in education. So here comes our core pillar of our offerings, that is Data Analytics Group. Within DAG, we provide a range of powerful tools and services focusing on statistical analysis. For statistical analysis, we have SPSS, StatCraft, and Atlas TI. And for optimization, we have Lingo, What's Best, and Lindo API. And also, at the heart of our mathematical modeling capabilities lies our expertise with Maple, that is Maplesoft. Maple is more than just a computational tool. It's an environment that empowers researchers, educators, and students to explore, visualize, and solve complex mathematical problems with unparalleled efficiencies. So, just to give a brief introduction about what Maple or Maplesoft is, our Maple portfolio encompasses the full suite of Maple products, including Maple Calculator, Maple Learn, Maple Flow, Maple Sim for simulation, and Maple as a desktop software. Maple Flow is majorly used for intuitive calculation management, and Maple Learn here is for interactive learning, which will be majorly used by professors, students, as well as researchers. And Maple Sim is for the simulation and physical modeling purposes of any uh, data or circuits. So we provide end-to-end support from licensing and implementation to training and customized solutions for entire Maplesoft portfolio that is visible here in the screen. And all our clients have been from IIT Kharagpur to IIT Jammu, DTU, Delhi University, IIT Delhi, and much more. Many more clients have been users of Maple. So this was a just brief introduction about binary semantics and Maplesoft. Just to begin with, how Maple works with all the academics and how exactly it is helpful for the professors and students. I'll be showcasing some of the basics in Maple, and also I'll be introducing you with the student success platform, which is majorly used by professors and students. After that, I'll be handing over to Anil sir. Professor Anil will be showcasing some of the basics in robotics and kinematic analysis. So to begin with, I will just brief about what Maple is. Maple is a mathematical tool majorly used in solving mathematical problems, starting with basics of expressions or any kind of simple logarithmic equations, polynomials to advanced mathematic calculation like linear algebra, calculus, differentiation, and integration. And as you can see, so this is the main environment of Maple, where we have two modes. One is of document mode and the other is of worksheet mode. Document mode is majorly used for the purpose of documenting or kind of creating any question papers, assignments, and also reports for researchers. In the meanwhile, if we talk about worksheets, worksheet is majorly used as an interactive document where the entire work that has been done or calculated can be documented and also visualized with a very computational or interactive way. So we can say it as a live computational space. So I'll directly delve into new worksheet mode. So this is the main interface of Maple, where we have the ribbons, which basically says about inserting, editing, view, evaluation, tools that we can use, different features that is available in Maple, which I'll be walking you through, and also regarding the education ribbon, if we talk, it directly delves us into all the topics majorly covered in the mathematical calculations. And also the workbook, which can be used once the workspace is used, and the help command, where we can directly check for the updates and get into Maple portal what's new in the Maple. Everything can be directly fetched from the help ribbon. So these are about the ribboning part. In Maple 2025, also we have in the interface, the left hand side is about palettes, and the right hand side that will be getting is context panel. So this is the main interface of Maple, as I said. And I have prepared a simple slide kind of a presentation kind of a thing using Maple itself, so that I can familiarize you all with a presentation part that can be used in Maple, where we can use the sections over here as I have used for basic features. For example, the interface and navigation, everything, these are called the sections that can be easily used. And also to start with some simple calculation and to introduce you to how to use Maple. Maple is a clickable interface and also with a drag and drop feature. So if suppose we are solving any simple polynomial or any kind of expression, then we can directly click on an expression palette and expand the expression palette and take any of the expressions that we want. Say I will work on 3x plus 5. So once the context panel is expanded, you can see in the context panel, as soon as I entered the equation 3x plus 5 is equal to 0, a simple equation, the context panel changes as per my input. So suppose if I want to...
Ma'am, the PPT is visible, only PPT is visible, your screen is not visible. There are some message from the participants also that only PPT is available. Means they are not able to see the screen. You can share complete screen.
Yeah, 1 second. Okay, so now is it
now it is visible. Yes, sir.
Hi Nitashri, can you start off again if possible? Because now
Yeah,
the
sure.
screen is visible. Yeah, thank you.
Sure. So as I was telling, this is the environment of Maple. 1 second. So this is the main environment of Maple we will get once we double click on Maple software. And we'll be getting two options. One is the document mode and the other is the worksheet mode, where the document mode is majorly used for preparing question papers and assignments, as I said before. And worksheet is a live computational and visualization interface. Once we get into worksheet mode, we'll be getting into main interface of Maple, where on the left hand side we have palettes. You can see in the palettes we have expressions, calculus, and other palettes as well, which we will use further in this webinar. And in the right hand side, it is context panel, which changes as per our input. And also Maple 2025 is made of a ribbon kind of interface, where we can just hover around in each ribbon and insert all the calculus or any of the palettes that is required. We can directly enter into these ribbons of tools, evaluation, education, workbook, and just explore this palettes and packages. I'll be showcasing one by one in this. So just to let you know, this is the main interface. And as I was talking about expressions, and the screen was maybe not visible. Now I hope everyone are able to see the screen. And once I give some simple equation as my input, that is 3x plus 5 is equal to 0, you can see like in the context panel, there are n number of options or operations that we can do or that we can operate upon the equation that we have given as an input. Say, suppose if we have to solve for x, then directly we can solve the same by clicking simplify or solve for variable x. So it basically Maple is a clickable and drag and drop interface with n number of palettes and packages that are available by default. We need not write programs or functions for those. This is one case. And in the expression palette, there are again about logarithms or any trigonometric functions like uh, sine of x. If I enter, then it does give other options like what we can do based on the input we have given. Sine of x can be both differentiated and as well as integrated. So we'll get those two options as well with respect to x. That is also possible. So this was about expression palette. Also, I would like to showcase, like I have created a presentation in the Maple itself so that I can familiarize you all that presentation with Maple itself is possible. Like we can add such sections where we can easily expand the section and collapse the sections whenever required, and easily that can be used as a presentation point of view. This is one of the options in Maple. Also, to move further with the other palettes, if I hover around and go to next palette, that is the calculus palette, here also directly we can get into many options, starting from ordinary differential equation to partial differential equations and also integration. When in a similar way, when we talk about differentiation, we have two options over here. Like we can make use of palettes or we can directly insert the derivatives over here. Like by using palette, we can also give the function here. Say I'll give sine square x. In the similar way, we can also use calculus palette for partial differential equation like dou square by dou x square. Any double derivatives also will be obtained. In this, if I take an example of a triple integration and give a function that is x plus y plus z with respect to x, y, and z, in the context panel, we get options to simplify, solve, or get the expansion for this. Anything can be operated based on our requirement. Evaluation, everything can be done. Or else, if we directly need any solution, then once we click on enter, then the triple integration of the function that we have given x plus y plus z will be obtained directly. Once we click enter from our keyboard, that is also possible. So these are some of the basics of expression palette, maybe some from calculus palette. In the similar way, if we go for matrix palette, there is an option of rows and columns where say suppose we have 2 cross 2 matrix, And there is also option for getting identity matrix, zero matrix, or random matrix that we can directly insert into the workspace. And you can see the options that we got for expressions and differentiation changed, and we can simplify matrices as per our requirement. Say we want to do some standard operations like finding the determinant of the matrix, then directly I can click in the context panel. I can go to standard operations and click on either adjoint of the matrix, determinant, inverse, anything. Say I go to adjoint of the same matrix, then adjoint of the matrix will be obtained. So in the similar way, for other solvers and forms in the matrix, we can convert the same matrix to row echelon form, Jordan form, where a reduced row echelon form is also possible to create by just clicking through context panel. So these are some of the basics that I could showcase using context panel. To move further, about how calculus can be explored and how differential equations can be easily solved. I'll be showcasing the same. Later we will walk through the plotting, and we also can do animation in Maple. We'll be walking through that, and of course some of the major features of Maple. Just to showcase the differential equation in Maple, say we have a random differential equation that I have already entered here in my presentation workspace. I'll be copying the same, and here copy pasting in Maple is as similar as how we do in any of the Word or Excel document. In the similar way, we can copy and paste the same equation here. So this is our differential equation, where we can classify the given differential equation. Like suppose we don't know what kind of a differential equation it is. Is it a homogeneous equation or a linear equation, anything? Then we can classify the differential equation, and it will redirect us to a page where it gives the examples similar to that, and also some kind of a description similar to that. Also, it says like the equation that we have entered is second order linear differential equation. In the similar way, if I take an example of to solve one of the equation, I will just enter it so that you can just get familiar with that. We need not to enter any of the differential equation in the workspace. We need not write any different command or functions. Just directly y double dash plus 2y dash plus 4y is equal to cos of x. This is just a random equation that I have entered. So we need not write any function or get into some programming commands or anything. Just like how we write using pen and book, in the same way we can write in Maple. We can directly type it, and once it is typed, we'll get options as we have got for other operations that we did before. In the similar way, we'll get n number of options starting from how we can solve this particular differential equation. So if I get into in this same context panel, once we scroll down, we'll get options to solve differential equation directly with respect to y of x, or solve differential equation interactively. Once we get into solve differential equation interactively, You can see we can give the initial and boundary conditions over here. The dialog box will be prompted where we can give the initial and boundary conditions for the differential equation, where I'll give randomly y at x is equal to 0 as 1 and at x is equal to 1 as 0, and we can just add all the conditions directly from this, and it can also be edited if required. Once it's done, I'll give done, and here we have two options to solve this particular differential equation. One is to get the numerical solution of the same, and the other is to get the symbolic solution of the same. So numerically, once we go, like this particular equation that I have given is the option where we'll not be able to solve numerically. So directly we can solve symbolically. To solve this symbolically, by default, it has been taken the transforms method, where I can just, other than the default method, I can choose transforms method where I'll choose Laplace transform or else Fourier transforms, any of it. And once I give solve over here, okay, so the equation I have given is the random equation just for example purpose. So the solution is not able to obtain. Now I'm entering the equation that I have pre-filled in my workspace, that is y double dash plus 5y dash plus y is equal to cos of x. And again, I'll be going to solve it by giving the boundary conditions. And it's done. So over here, when we go to solve this numerically, we'll be entering into one more dialog box where the equation that I have given is the boundary value problem. So it directly solves it at the function values at x is equal to 0.5. This also can be changed. This by default I've given to 0.5. This can be changed to 1, 2, 3, anything as per your requirement. And once we go to solve, numerical solution for y and y dash is obtained, and also plot can be obtained along with the maple commands for the same. So all these are the obtained solution for the equation that we have given, and on quit we can return with the numerical procedure or the plot. So once I click on plot and quit, the same solution can be seen, and this will be visible in our workspace. This plot again can be reset, or the legends or titles can be added, the legends can be changed, the manipulation of entire plot can be done easily. By clicking on the plot, you can see over here the scaling is obtained. So over here we can add the legends, title, everything to the plot. So this was about how we can solve differential equation numerically. In the similar way, we can also get symbolic solution. So Maple stands out when compared to other softwares like MATLAB or Mathematica. Maple stands out here where it can provide both numerical solution as well as symbolic solution. That is the main plus point of Maple, I can say. So to move further about plotting, just to showcase how 2D plots in Maple work, you can just see, like, this is also one of the 2D plot that we got for the solution. In the similar way, if I take one of the function like sine of x by 2 as my function, then we can directly get the 2D plot in the right hand side here, or else go to plots and select 2D or 3D plot as per our requirement. So once I go for 2D plot, the range and legends are pre-built over here. If suppose you want to set the range for x, then instead of going to plots here, we can also use plot builder, where we can set the entire ranges, change the range of x, where it is by default taken from -2 pi to 2 pi. This also can be changed. All the basic options like color, style, legends, axis, thickness of the curve, everything can be changed with the plot builder option. So this is one of the uh, examples for 2D plotting. In the similar way, for 3D, if I take an example of one of the functions, say x square plus y square, then again in the plots, we can get into 3D plot, where directly we can fetch 3D plot for the function that I have given, x square plus y square. And for the same, the orientation and the transparency, the legend, everything can be changed by using these scaling constraints over that is available here. All this can be done for 2D and 3D plots both. And if suppose you are working on some paper and in mid of any functions or something, you will have to plot and again come back to the text mode or the calculation mode, then directly that can be entered with just a click here. If we click on the cursor, we can enter into the text mode. So that is also possible. Other than this, the next topic after plotting is about visualization and animation. Just to showcase the animation, I'll just showcase it over here as there is little bit of time constraint. So if I talk about 2D animation under visualization, here the animation works similar to the plotting, where we'll be giving this particular example I have taken is to animate a curve or a surface on a curvature on a parameter. So you can see once we have plotted, if I the ribbon will get into animation ribbon directly, and I can play this and the animation of the curve like this on a surface, the same animation can be viewed. In the similar way, 3D animation for the same also can be viewed when the entire plot for the 3D animation is done. Here I have taken the function of x square plus y square to animate a curve on a parameter, same. So this is how it can be done directly by clicking on plots and 3D plots. In the similar way, animation also can be done. Moving further with some of the key features of Maple, the major feature of Maple comes with the ribbon, where directly we can make use of any of the required features or options as per our requirement. In the similar way, when we come under Tools ribbon, here we can get n number of packages that is already available with Maple, like starting from graph theory, linear algebra, signal processing, also physics and chemistry, dynamic systems, discrete transforms. All the packages will be available uh, free of cost along with Maple subscription. It doesn't require all this library of packages doesn't require extra purchase or anything. So that is one of the major thing about packages in Maple. So when we talk about major feature in Maple, that is the assistance. Main thing is about code generation assistance, where in the code generation assistance, we can translate the Maple code that we have given as an input to any of the output, like any of the required language. Say we are working in some project where we have integrated Maple with MATLAB. So Maple can be integrable with MATLAB, Python, and R. So once we have integrated Maple with MATLAB, then directly we can fetch the code, or else even though if we have not integrated it or we are working separately in some other software, the code can be translated. Once we copy the Maple code over here and paste it and give the translated output, we can fetch it in Java or else MATLAB or even Python R. And the same code directly we can copy in the similar way and paste it in our required interface. Say we are working in the Python interface also, then directly this can be copied and pasted over there. So this is the major feature in Maple that is available, where we can easily generate or translate Maple code to required code from C, C Sharp, Python, R, and also MATLAB as well. So this is one of the major features of Maple. Other than this, we also have an option of Maple Cloud, where the entire workspace that we have been worked upon, say this is the worksheet that we have worked since 20 minutes now. So this can directly be saved and saved to directly cloud, Maple Cloud here, and that can also be viewed by anyone who is not using Maple. Say you are sharing your research paper with one of your students or anyone who doesn't have Maple, then they also can view it. Maple Cloud has an option of view, giving view to others who doesn't have Maple. Other than this, we have latex that we can convert. Say we are working on some research paper, then directly the entire research paper can be converted to latex environment. That majorly possible for researchers who are working on some research papers. Then directly this can be converted to latex environment. And other than this, the entire page can be exported into PDF, JPEG, and all other formats that is available. So entire workspace can be exported. That is also possible. Other than this, if I move further, we have one more option, that is the map apps, which are majorly designed to illustrate various mathematical and scientific concepts under Maple. This is available in the education ribbon itself, where directly I can go to education ribbon over here and fetch math apps. Once I click on math apps, you can see the entire visualization for these many topics, starting from algebra, basics, calculus, graphing to trigonometry, and also natural sciences like physics and engineering applications is available over here in math apps. If I click on one of the options, like you can also see subtopics relevant to calculus over here. So these are some of the major features in Maple. Other than this, Under education, as I said, we have a number of other subtopics starting from statistics, optimization, numerical analysis, graph theory, and much more. To further quickly talk about some of the apps that is available, that is directly we can fetch from the study guides, where we can go for the Maple portal for students over here and get into the study guides and the entire portal for students, and student relevant topics will be available here, which we can make use of for either to learn Maple or to work upon it. Both for those reasons, we can make use of this student portal, Maple student portal or Maple portal. And also, we have in Maple 2025, the advanced feature that has been introduced is the, other than this ribboning part, the major part that has been introduced is AI and NLP. So AI formula assistance, as you can see, is visible over here in the left hand side, AI formula assistance. Here, once we describe any of our formula or equation or any relevant topic, then we can directly help students or ourselves, whoever are working in Maple, can take help of this AI assistance and work upon it. Say, suppose we are working on some surface area of a circle, and give search. Then this AI is backed by GPT-4. It directly leads to GPT and fetches us relevant descriptors related to surface area of a circle that I have given as a topic as a input, and it within some time it gives us the area formula. It has been given area formula and also some of the description related to that. In the similar way, we'll get the drop down like this, where we can get into integral representation of the surface area of a circle, circumference form, everything. And this formula can directly be imported inserted in the workspace, like with the clickable button over here, insert formula, we can get into the um, insert formula. We can insert this surface area as well. So this was about a new feature in Maple 2025, that is AI feature. And this was introduction and some of the basic feature introduction regarding Maple and how exactly this can be used. And as you have seen, Maple 2025 is not just about how powerful the computations are, it's also about creating more supportive and efficient environment for complex problems in both basic and applied mathematics for students, professors, and researchers. I have, as I'm running out of time, I'll be handing over this to Professor Anil Kumar, sir, now, and he will be delving into the practical applications of Maple now, showcasing how these modern tools are used to solve real-world problems in engineering. So, Anil, sir, over to you.
Thank you, ma'am. Now I think the PPT is visible to all. Hello.
Yes, it is, sir.
Now, uh, good evening now to all. I will be presenting some basics of kinematic analysis which are being used in robotics. Starting with the first, what is kinematic analysis? Kinematic analysis is finding the relative motion between the links. The robots are made of different links or parts. They are moving relative to each other, and finding out the relative motion is the kinematic analysis, and in that we do have two types of kinematic analysis. One is moving forward. Sometimes we call it as forward kinematics, or we call it as direct kinematics, where we are moving from base to the tip of that robot. And the other one is the inverse kinematics, where we know the final position of the tip of the robot, and we find out the required orientations. Now that can be presented in basic manner with this one, where we have to convert from joint space to the Cartesian. We are given if we are given with some angular motions, if we can consider this as a hand as a uh, robotic arm, if we know that how much we are rotating, that we call it as a joint space. And the Cartesian is something which we know that it is represented in form of x comma y. If we know theta, we can find out x, y, or z position of that particular link point, or we can say tip of that robot. If we are moving in the forward manner from the angular motion to the Cartesian part, xy position, it is known as forward transformation. And if we are moving back, if we know the final position of the tip of that robot, and we want to find out the required orientation of those joints, that is called as inverse transformation. And this is written in this PPT. And this is something which we can say that this is an example how we are calculating, if we know that theta 1 is given, theta 2 is given, how we have to calculate. Then the this is the first link which we can say, and it is being oriented at an angle theta 1, and this dotted portion, the angle with this dotted portion, is called as theta 2. If we are calculating this theta 2 as positive, we are moving in the counterclockwise direction. And if we simply say that, if in place of moving in counterclockwise, if I calculate in the clockwise direction, the theta will be negative, and we have to use that sign sign for that theta. If it is negative, minus theta 2 will be used, and we can calculate in this. And if we move in this uh, manipulator kinematics, we will see that we have to find out the final position with respect to theta 1 and theta 2. And for that, we will use the trigonometric function. And this is the basic presentation of that PPT. That two link mechanism is there, where the length of the first link is L1, and the length of the L2 is given. And the first link is oriented at theta 1 angle, and the link 2 is oriented at theta 2. We will take first part L1 as the first part to be considered. In that, the x-axis is there. On that, we will find out L1 cos theta 1, and y-axis we will calculate L1 sin theta 1. This is basic trigonometry. And if we want to find out the final position after L2 length, then we can say that this is having two components. One is due to this theta 1 orientation of L1, and the another is due to the theta 2 orientation with respect to theta 1. And if we calculate the total angular displacement of this L2 with respect to the initial position of x dash, then it will be the first theta 1 which will move it to the dotted positions. And then after that dotted position, the link will be oriented again for theta 2. The total orientation will be theta 1 plus theta 2. We can see that this Cartesian coordinates can be written as L1 cos theta 1 and L1 sin theta 1 for the first link up to this first point A, or we can say that this first point where the arrow is there. And then if we want to move to this next level, then it will be L2 cos theta 2 plus theta 1 plus theta 2, because the total orientation is theta 1 plus theta 2. The movement or the orientation with respect to the new position for the tip of L1, we can say that the relative motion will be L2 cos theta 1 plus theta 2 and L2 sin theta 1 sin theta 2. And we can move with this and we can add these two to get the total, or we can say the resultant R to R. We can say that R1 is up to some position L1 cos theta 1, L1 sin theta 1, and L2 is this one, last position of this manipulator. If we add these two, we will get the final position x comma y. And this we can write it as L1 cos theta 1 will be the first R1 for x position plus L2 cos theta 1 plus theta 2. Similarly, we can write for y position R1 y plus R2 y. We can simply add these two, means R1 can be written as x1 y1, R2 can be written as x2 y2. Then we can add x1 plus x2 as x and y1 plus y2 as y. This is basic. Now, if we want to move back, means from if we know the final position of x comma y of that manipulator, we have to determine the positions of these two links so that we can finally reach to this x comma y position. This orientation we have to calculate, and this is used in control system of robotics, and which we can say that if we are moving in this pattern, it looks very difficult for us to move in calculate the theta position. But when we will move with this, we can say that if I want to move to some position at x position, I can move from the below position also, and I can pick that glass, or if we have some glass on the top of this table, I can pick it up from the top, or I can pick from the bottom. We do have different orientation theta 2. It may be negative or it may be positive. Based on that, we will calculate the theta 1. And this we can see from this position that we already know that this is x comma y L1 cos theta 1 plus L2 cos theta 1 plus theta 2, which is elaborated in this one, which is expanded. And if we simply square this x and y and we compile all those equations, we will get the expression for this cos theta 2. And this gives us x square plus y square minus L1 square plus L2 square divided by 2 L1 L2. This will be the final expression where x and y we already know, and L1 and L2 are our symmetrical constants for these link lengths. Now, if we want to calculate this, we already have calculated this theta 2 position. Uh, this theta 2 position we have calculated in this. And once we know this, we can say that this is beta is the angle which the tip of that robot will be making. That angle is our beta. This we can easily calculate as a means right angle triangle. We can have beta angle, 90-degree angle, and everything. From there, we can calculate tan beta as this expression y by x. We can directly use this, and after that, this tan alpha is also similar to that. And the only condition is this, that this is the right angle triangle. In this, we will calculate alpha angle. This alpha angle we can simply calculate by using this is our L, L2 cos theta 2, and this total length, the base will be our L1 plus L2 cos theta 2, and the perpendicular will be our L2 sin theta 2. Based on this, we can calculate tan alpha. And if I subtract this alpha from this beta, I will simply get the orientation of the first link. And this is taken as theta 1 is equal to beta minus alpha, and taking tan theta on both sides and putting elaborating or expanding this form and putting these values, we will get the expression for theta 1. And this is our theta 1 where we can calculate because we already know that this is our cos theta 2, means we have a theta 2 angle, and based on that we can find out sin theta 1 and cos theta 1. Um, then we can move with theta, means theta 2 we already know, then we can calculate theta 1. And this looks very simple, and based on this we will move with the how we make the, means how can we represent the location or the point in the space in a matrix form. This we can see that if we can say that this is the point P or which we want to represent, uh, then the vector will be our AX I, a unit vector I, plus BY unit vector J, then CJ unit vector K. We can represent this as basic vector, means this uh, vector form vector, which will be represented in the arrow starting from the origin to the P position. This we can write, and based on this we can move write this in this form X, Y, and Z system, where we have to move in this X axis, then we are moving in Y axis, then we have to move in Z axis, then only we can reach to the point P. Now, moving to the next portion, we do have three axes, X, Y, and Z, and we do have three means unit vectors orientation O, A, and N, and this we can write in this pattern NX, NY, and Z, some unit vector which are mutually perpendicular. We can rotate this frame at the origin itself. We are having NX, NY, and NZ. It is one vector. Then orthogonal vector is there OX, OY, OZ, and AX, OAY, and AZ is our approach vector. We can write in this form, and this matrix will be our 3 by 3 matrix. And this is the style which we are using for presenting the positions in terms of matrix. And this matrix solution will be taken in Maple itself. If we are moving from origin to some position through this vector P, then we can get this type of matrix where the same matrix and normal matrix, and normal vector is available, orientation vector is available, approach vector is available, and these are px, py, and pz. These are the distance which are being moved. These are the positions type of thing, x, y, and z positions, and this one is there. Now we can say that px, py, pz are our position vectors, and this nx, ox, ax, ny, oy, ai, this dotted matrix, we call it as a rotation matrix. And once we rotate something, cos theta and sin theta term will come into the picture. The next one is our 0, 0, 0 portion. These are our perspective transformations which we will be using. Means this complete 4 by 4 matrix is having 3 by 3 rotational matrix. Then we do have 3 by 1 position matrix or position vector. Then we do have 1 by 3 perspective transformation matrix, and this one we call it as global scaling. If we want to present in 1 to 1 ratio or 2:1 ratio like that, and normally we put it as 1. Now we will be solving for 1 by means 4 by 4 matrix. Now, how we are getting these type of these matrix when we are rotating from one point origin to the tip of that position. Now we will move with the this one. Also, the inverse calculation is easy for our 4 by 4 matrix, means square matrix. We can do inverse easily, and that will be used for calculating the reverse of that portion. This is what I want to move. If we are having one position at this point, and I am moving with translatory motion through a distance d, then new position is achieved at this position. new position will be there, and it is being translated. No orientation is conducted about normal orientation or approach matrix. Only translation is being done. Then the rotational matrix will be an identity matrix, and the change from this position to this position will be here dx, dy, and dz. This will be our transformation matrix for pure translatory motion in space. There is no rotation of this matrix. Now moving with the next will be there. This is something which we have discussed, where we are moving from P. If we are moving directly, nothing is being changed from orientation to this position. Only translatory motion is done through Px, Py, Pz. We are putting like this, and this we present it as T, starting from R to P. Now, if we are having this one, translatory motion, then we do have three translatory motion about x-axis, y-axis, and z-axis, and three rotatory motion about those axes. But normally, what we are doing, we are taking only translatory and rotatory motion about x-axis and z-axis only, and y-axis we do not take into consideration. For that, what we are doing, we will calculate all the transformation matrix. We will get the transformation matrix, how we are moving from orient this point O to the final position of the tip, how it is being oriented, it is being rotated, and it is being translated. What will be the sequence of this orientation translation that we will take into consideration, and based on that, what we will be using, we will be basically taking three. The basic multiplication will be orientation about z-axis, then orientation then translatory motion about z-axis, then translation about x-axis, then orientation about x-axis. That will be our sequence when we will be calculating the composite matrix, or we can say that from one link to the last point, there will be some sequence of orientation or translation. That for that we will be calculating one composite matrix, and that we can do. Now here, what we are having cylindrical coordinate system, where we are using alpha angle, which is being oriented about z-axis. This is our z-axis, and this is our alpha angle presented here. Now we will be writing C alpha as cos alpha minus sin alpha and cos alpha, and based on this, we can say that there will be translation R cos alpha and R sin alpha. This will be our translatory motion about this, and we will be getting different orientations about z-axis, y-axis, and x-axis. But we will be using only two or rotatory motion, one translatory motion for reaching to some particular position directly. Now we can say that this will be our composite matrix. Now, if we talk about the DH representation, there will be a multiplication of these matrix. Means we can calculate directly, and based on that, we will be doing some orientation of this type of thing. And in that, I will go to this picture where we do have nth joint, which is connected. This is the first joint which is there, and it is connected to the nth link. Nth joint is connected to nth link. Then we are moving to the next link, which is n plus this theta n plus 1, and then this is connected to n plus 1. Then there is also again orientation theta n plus 2. We are having one reference plane. Then we are doing some orientation and translatory motions, translatory operation, and we will be reaching to this n plus 1 position, and then we will move to the n plus 2 position. Now this is our nth joint which we are interested in this. In this, what we are doing, we are having this axis is there. We rotate the axis in the counterclockwise direction. Because the axis is in this direction, we take the right hand thumb rule. If we point the thumb in the axis position and the fingers will be pointing the orientation, positive orientation of that link. Now
Till time, if you would like to say something on the maple, that will also help the attendees to gain more insights. Till the time he joins the
Yes.
network.
Uh, so I just want to tell about student success platform in Maple, where it is a platform that comes as a package. Where in Maple, there are, as I showcased, there are a number of tools in Maple portfolio, starting from Maple Calculator, Maple Learn, Maple Flow, Maple Sim. So Student Success Platform is one such platform where we can get access to all these tools at a time as a student and as a professor. Just to give a glimpse of it, let me share my screen until answer comes. So as I was telling, student success
yeah,
platform.
I'm available now.
Okay.
Yes, ma'am. There was some issue. Just disconnected.
No worries, sir.
Okay, so
Means,
I think instead of showcasing in PPT, you can
ma'am,
directly
it is
share.
just one or two slides and then it will be completed. Just after
Yeah,
that, I will.
sure. So
This is,
that they'll
again,
get more understanding through Maple.
yes,
So
ma'am, yes,
that's
ma'am.
what.
After that, I will start with this matrix system. This is our joint end, uh, which is being, I mean, this is our axis, and then this we can say that this is the this is being oriented about the z axis, and the orientation about z axis we take it as theta, and it is being uh, this is the link length n, which is the distance between the two parallel axes of these axes and these joints. This the distance we call it as a, and then we move to the next joint n plus one. Again, this is our axis. This is the translatory motion about an from joint n to joint n plus one. Now we can have again this if I am moving along the z-axis, we mark it as D, and this is or translatory motion from this position. If I'm moving from this position to this position, then I have to move to this position, this a n plus one. Then this axis, that is movement along the joint axis is our D point. Then we will move, we will orientate about this x-axis, and this is being represented as alpha angle. And we finally move to the final position from A to B with different orientation, starting with the theta orientation about z-axis, then moving along the uh, x-axis, then moving along z-axis, then rotating about x-axis. This will be there, and these are the different axes which we can say that being presented how we are moving, and this is an orientation and this type of thing. If we move in this fashion, and finally we get the composite matrix in this pattern. This is something which we have discussed, and based on this, we can say that the matrix will be this type of thing, where the orientation about z-axis will represent it as cos theta, minus sin theta, cos theta, and the z-axis is there. That's why we are putting only one. If translation is there, rotational matrix will be unit matrix, and the motion about z-axis will be put at pz. Similarly, translation about x-axis will be put at this 1,4 position at ln, and then orientation about x-axis will be kept in this pattern. And if we multiply all these matrices in this fashion, that first we will put the matrix for rotation about z-axis, then translation about z-axis, then translation about x-axis, then orientation of the x-axis. If all we multiply all these, we will get a complete orientation matrix in this form. Now coming to the mm, Maple part, these calculations are done easily in the matrix Maple portion. Now we'll move with that. I think I'll share the screen, entire screen. Now, if we move to the Maple portion, this is something which we have discussed in this complete seminar. Some theory of this robotics arm, everything is kept here, and then we will move in this pattern. This is our rotational matrix and this type of thing. And if we x-axis, uh, orientation about x-axis is shown by alpha angle. Orientation about z-axis is shown as theta angle, and we are not taking consideration of this a orientation about or y-axis because it is not a free. It is not in free space. It is being fixed at some point, and some restrictions are there. That's why orientation about z-axis is restricted in this. And these, what we have discussed in the DS parameter for presenting this one, we do like this. And if we simply write this in this style, that the total composite matrix T, we will write it as this double dot equal to. This will be assigning this multiplication of these four matrices in this sequence. We will get the final matrix in this time. This is the result which we are getting in this fashion in this type. This is something which we are getting due to the multiplication of orientation about z-axis, considering this theta, or in translation about d-axis, about this one, and about D, this one identity matrix followed by 0, 0, D, then followed by this matrix A or mistranslatory motion about x-axis, then this we call it as orientation about x-axis. And if we multiply all this is that simple that if we simply click equal means enter into this, then we will get this multiplication matrix, complete matrix, which we normally, if we solve, it will take more time and it is doing by simple mathematics. Now, if we take the example of a Puma robot, this is something which we do have. In this, we are having a basic base at 0, 0. It is being translated means about z-axis to this shoulder portion. This we call it as shoulder. And this shoulder is being rotated about means it will be called as theta. And if we are rotating about theta, first we have to translate from the 0 position through this z-axis through a distance of d0 to reach to this shoulder. Then it will be rotated, and this rotation will be our theta 1. Now this rotation will rotate this upper arm up and down, and this angle we call it as theta 2. Theta 1 will be something which we can say that if we are rotating the base, it will be our theta 1. The second one we can say that it is our shoulder, which will be rotating, and it will be moving our upper arm up and down. Then this is again connected with the forearm through another joint, which we call it as joint number 3. And this will again rotate. And the last, this one will be our wrist joint, which will be connected to the hand effector. And these type of robots which we are seeing here, Puma robot, it is being used in different industries. If we know the basics, we can do in this style. After that, what we are doing, we are simply drawing all the DS parameters which we have discussed, that how we will be moving from one point to another through this right hand rule. If I say that thumb is showing my x-axis and this middle finger is showing my z-axis, then the second finger, index finger, will be showing by y-axis. These three axes will be presented by this most style, that thumb, it is pointing out, y-axis, if I can say that it is outside, in it is on x-axis, this is our y-axis, then the z-axis will be pointing out of the screen. These will be our positive axis. And if we are rotating about, if we are moving to another portion, we will be rotating theta alpha angles. Means either we will be rotating about the thumb, or we will be rotating our second middle finger. And based on that, we will be saying that how much we have to move. If it is plus 90 degree, we will be moving, or it will be minus 90 degree if we are moving, to move to the new frame, and that will be there. Based on this, we can prepare this DS parameter, which is first point which we have to decide. And Maple is not doing anything in this. We have to use our basic concepts in this, and based on that, we will be using this one. Only thing is that we have done this one. We have got this metric. This matrix we have received, means we have calculated, we have got from the Maple. This matrix will be used here in this. We will be initiate different programs so that we can do some plotting and that type of thing. If we start this one, we will enable the linear algebra, plots, plot tools, and dynamic system, and then we can put evaluate theta is equal to pi by 2, because this is our pi, this is our pi, and this is pi rotation, alpha is our minus pi rotation. Based on that, we will be using this evaluation. We will evaluate this T1, T2, T3 type of thing. We do have 6 theta, and based on that, we will calculate 6 transformation matrix, which in itself include theta 1, theta 1, theta 2 up to theta 6, alpha 1 up to alpha 6. Some of them may be 0 or something like that, but everything will be calculated by these matrices at T1, T2, T3, T4, T5, and T6. And then we can say that if we multiply all these complete, then it will give us this big matrix, which we can see here, that this is that big matrix, which we can say, where theta 1 is there, theta 2, theta 3, theta 4, theta 1, theta 4, everything is available. And we can see that translation about z-axis of the sixth joint is also available. This big matrix will be calculated by the Maple itself. We have to program, and then if we multiply this complete transformation matrix with the base matrix origin, this is our origin vector, which we can say that this is our origin position vector. 0 0 0, this is our origin, and to multiply it with this 4 by 4 matrix, we will make it to 4 by 4 matrix, 0 0, and this one. And then if we multiply it, we will get this type of matrix. We can get in this type directly if we multiply this T1 6 to this one. This is our matrix which we T1 6 to this one. Then what we can do, we can decide the and effector, the path of that and effector, we can decide that how it has to move. And that expression I have taken from Maple itself, some program is there. I didn't change. I used that directly. And based on that, we can have this orientation X, Y, and Z, how it will be moving with respect to time T, that path we have to define. And then we can say that if we want to differentiate, we will use this expression directly from here. We can use these expressions, we can use these calculus from here itself, that differentiation, but madam has shown. I use these expressions from this type of thing only. And based on these calculations, we can get these big matrix and we can draw if required. This is something which we do have in this. We can use these metrics. We can plot these because this is the mathematical modeling part. We will be getting different plotting graphs itself. Some issues may be there. I mean, this is some different software. I got some issues, but it is being used. It is very helpful in this calculation. And as we can plot from this directly, we do have plot graphs also. If we click, we get plotting also. 3D, we can plot 3D graphs also, we can plot 2D also from here itself, and we can use matrix to find out the if I can say that if I'm using this matrix, I can say where it is. If I want to invert this matrix, sometimes we will be using this inverse matrix in this also. If I say that I want to invert this matrix, I will simply where it is. We can invert from a something is there. I forgot. This is matrix. Something is there. Yeah. We can use inverse of this matrix directly. We can take the inverse. It is means it is not visible right now, but we can directly from this matrix it was available. In ma'am, hello, ma'am. I think uh, I want to show this inverse, but it is not visible right now. If I can find out. Means on the right hand side, no, it should be available inverse of this, but it is not showing. But if I click here, it's should be on the right hand side. I cannot find out right now.
Standard operation.
Yeah, it should be there, but convert to equations. It was there. It is using these equations. It is direct. If I want to show something, it should be there. Now it is changing. Something is there. Some software issue may be there. Now it has been changed to this type of thing. Something may be there, but matrix I can tell. This I can have and we can put here. Right. Control Z. Control D.
So maybe you have got
Copy.
some software issue or
Ma'am, it is some issue I am.
software slow.
Ma'am, sometimes it sometimes yeah, sometimes there is a issue with this one. Yeah, and now it is there.
That's fine, sir. So
Yes.
maybe due to slow.
Yeah, now it is there. Yes, sir. If I want to take the inverse of this, it should be available on the right hand side. Or sometimes we right click on this also, it should be available. For taking inverse eigenvectors and everything, it should be available in this. If I right click on this, then it should be available. But some issue is there with this software. We can write it as AZ inverse of A Z. Now, see, ma'am, it is not showing inverse directly. It is writing inverse of this AZ. It is taking. Normally, it should do this.
So maybe at your place there is some internet issue, and as you know, we are running out of time also.
I am, ma'am. We
So
can
just
complete. We can wind up.
conclude this.
Yeah, you can conclude, ma'am. Some issue is there. It is okay. Some inverse will be there, but we can use this in this matrix. Normally, we will be using inverse, transpose, and everything will be available on one click. Right click of this, everything will be available. Now, this is something which I wanted to introduce. I wanted to show some, tell some basics about this. Uh, this is over from my side. Something is there, it is not taking. I will stop here.
Okay. Okay.
Never
Okay.
mind, sir. That
Maybe
was really nice.
there is
Thank you so
some
much for that.
internet.
Please continue, Nitya.
Maybe there was some internet connectivity issue or slow internet from your end, sir. No problem. But how much ever you have showcased, thank you so much for that, Professor, sir. Like your expertise and demonstration has really helped many of the students to understand the practical applications of Maple. So we now have a little bit of time for question and answer if anyone wants to ask any kind of question related to Maple, its features, or any comparison related to Maple or other mathematical software. You can please type your queries in the chat box so that we can quickly address it. Other than the solution, other than the queries it's been asked, any other queries, if anyone wants to ask, you can quickly share in the chat box. So that could be addressed. Okay. Okay, I hope there are no other queries, or if at all you get any other questions further, if you are getting into Maple website and you are trying it on your own, then you can directly connect with us, that is binary semantics. Any of us, like our manager Arun Kumar and also our sales manager Devin Sharma is available over here. So I thank each and every one of you for your support for accomplishing this webinar. Of course, we have covered a lot in a very short time, and that's the reason that Maple is, of course, a very vast topic in mathematical computations and everything. So we could just give a glimpse of what exactly it is. Our manager, Arun Kumar and Devendra Sharma is also here. So, any words from your end, sir?
So thank you so much, Nitya. Professor Anil Kumarji, thank you so much for this wonderful session from your side. I'm sure it is very interesting and you have given a lot more knowledge to our participants and attendees to work on Maple solutions for you. Perfectly.
Yeah, sir.
Thank you
Because
so much
it
for
is
this part, sir.
basic. It was very basic because unless we do not know that why we are studying matrix, it will be of no use. That's why
Absolutely.
once we have to go to the matrix, then how it is being used in the industry point of view or research point of view, then any operation on this matrix, maybe differential, integral, or something like that, everything which will be used in this computation part, that will be
Absolutely.
useful once you know the application.
Absolutely, sir. I'm with you on this one. So thank you so much for that. And attendance, participants, thank you so much for bearing all of us